talk is from Matt Nobriga. He's going to talk about the Delta Smelt biological opinions.
All right, hit it again. It's on, isn't it? It's on. Well, while that's queuing up, I'd like to thank the science program for the opportunity to speak this morning, and I'd like to thank the panel for listening to my spiel here this morning, and also acknowledge my co-authors, Catherine Sun and Aaron Gleason from the regulatory division in our office, because this presentation could not have gotten put together without them. It's been a pretty hectic couple of weeks. So I'm not really going to talk about the biological opinions in any big picture sense. I'm going to talk mostly about Old and Middle River flow, because this is an interior delta flows workshop. And excellent. This is a quick overview of the talk. Sam asked that we think about presenting a conceptual model to the panel so that they could understand the bigger picture, and always wanting to aim to please. This entire talk's going to be a nested series of conceptual models, some of them moronically simple, some of them slightly better than moronically simple, hopefully. And it's organized kind of like this. What is OMR flow? Just get that out of the way and give people a sense of the system. And then back way out and talk about the universe of ecological stressors in the Bay Delta a little bit. And then focus on the interaction of Central Valley Project and State Water Project operations with the biology of Delta Smelt, having thought about the context of that bigger ecosystem. And then lastly, why the Fish and Wildlife Service used Old and Middle River flow, or OMR flow, in our biological opinion for the water projects. So take-home points, just to get these in your mind to think about. It's a clams estuary when you think about the fish assemblage of the estuary. Secondly, the OCAP biological opinion focused on Old and Middle River flow and delta outflow, because project operations were the scope of that consultation. And lastly, this is just a slight rephrase of what we submitted to the state board in 2012, which is that we think that Old and Middle River flow is the best available flow metric to characterize or conceptualize entrainment risk for Delta Smelt. So what is OMR flow, or Old and Middle River flow? I wish I had a laser pointer, but I don't. So hopefully I can speak to the map. Which one? Oh, the top one. I do have a laser pointer. Awesome. So we have the Golden Gate Bridge in San Francisco there. That's where the Pacific Ocean comes into the San Francisco estuary. And then we have the Sacramento. You're right here by the W, more or less. And the Sacramento River's flowing into the Delta, and the San Joaquin is flowing into the Delta from here. And they're mixing in the Bay Delta estuary. The ocean and the rivers are mixing in the Bay Delta estuary. The blue channel here is Old River. The red channel is Middle River. The state and federal water project pumps are down here in the southern part of the Delta. They're pumping water that is tidally influenced, but as I'll get into in a bit, this whole entire part of the estuary is kept fresh water to support the export of water from the Delta, south of the Delta. And so Old and Middle River flow, as its name implies, is the flow in these channels. It usually gets considered as a tidally filtered net flow, but it isn't necessarily that, and I'll get into that. And usually a tidally filtered net flow over daily to weekly time scales. And OMR flow, as it gets used in a regulatory context, is actually typically the sum of the two tidally filtered net flows in those river channels. So just a quick punchline about why Old and Middle River flow as opposed to other delta hydrodynamic indices. So these are scatter plots. These are scatter plots of export to inflow ratio, which is part of the existing Delta Water Quality Control Plan, versus Old and Middle River flow on the y-axis. These are, most of my talk is going to focus on adult Delta smelt during the winter, so these are just December to March data, just to keep in mind. And then over here you have Q West, which is an even older metric. That's the net flow in the San Joaquin River at Jersey Point, which maybe I can go back to the map really quick. Jersey Point is about right there. So the punchline is that the export to inflow ratio and OMR are not really closely linked. The top panels are daily time scale, and the bottom panels are monthly time scale. The red triangles circle points where the data are pretty incomplete, just in case there was something looking like an outlier. So at a very low export to inflow ratio, there's pretty rapid response in terms of OMR, and then it flattens way out. Q West and OMR are correlated to the tune of about a Pearson correlation coefficient of 0.7 viewed over enough range of data. But most of the data are down here where you can't see the individual data points, and they're not incredibly closely linked there. So Old and Middle River flow is closest to the projects. It's most manageable by the projects. And so this is part of our rationale for why we've used that as the metric. So now I said I was going to back way out and talk about the ecosystem, the estuarine ecosystem. So just conceptually, this is one of these moronically simple conceptual models. There's a universe of ecosystem stressors, impacts, state changes, sources of incidental mortality, and the like. And in a Section 7 consultation, those tend to go into the environmental baseline. There are things that we consider that affect the status of the species as the consultation happens. But they are not in and of themselves the consultation. And at the ecosystem scale, I think that the big overriding stressor, if you will, is the invasion of the estuary by the overbite clam in the latter 1980s. This figure comes from a recent paper by Jim Clorn and Alan Jasby that was a very excellent ecological synthesis of the system. And this is a great figure to show lower trophic food web changes that coincided with the invasion of the overbite clam. Clam arrived in 1986, and when that happened, the chlorophyll tanked, the rotifers tanked, this copepod tanked, and the mysids tanked. So the entire food web underneath planktivorous fishes. Well, then the question is, what about the fish? Yeah, them too. This is a time series of fish catch per unit effort on the y-axis. You're on the x-axis from the California Department of Fish and Wildlife's fall midwater trawl. And it shows the same step change, coincident with the overbite clam in 1987. Most of the catch in the history of that trawl has been northern anchovy. Northern anchovy occur up and down the Pacific coast. They're a mainly marine fish. They used to use the low salinity zone, even though it was physiologically stressful for them because there was a lot of food there. When the food wasn't there, they left. So that's not really a fish decline, that's a fish movement. But for some of the other fishes that are on this list that are more dependent on the low salinity zone of the estuary, their ability to move, they have some ability to move, but it's far more constrained, and so there has been decline associated with that change. This is actually a plot of the top 7 most abundant species, and I picked 7 because on average Delta smelt has been the 7th most abundant. It's colored in white, and it's on that plot. If you're in the back of the room, I guarantee you cannot see the relative abundance of Delta smelt in that time series. The panelists may be able to see it a couple of times during that time series, so it's a rare fish, and it's been a rare fish for my entire lifetime. And so it is kind of a proverbial needle in a haystack in this estuarine ecosystem, and the needle might not do exactly what the haystack does. So this is the Department of Fish and Wildlife's official fall midwater trawl index of relative abundance of Delta smelt, pulled out of that other time series so that you can see it. And I've got the bars colored so that black is above the long-term mean in that time series and white is below it. And main point being that Delta smelts declined in 1981, 5 years before the overbite clam invasion, 6 years before it had any measurable effect on the ecosystem. It has spent most of the time in the last 32 years, 33 years, with a negative population growth rate or below its long-term mean, with a little rebound in the 1990s. So when we do a consultation, as we did with reclamation for the water project operations, we understand this universe of stressors that's out there, these ecosystem changes, and then we have to consider the project that's proposed to us with that as background, but think about the interaction of that. And so some of the OCAP consultation is outside the estuary and outside that discussion, and some of it's within it. And it's really this area of action that our reasonable and prudent alternative focuses on, or this, and this is just a conceptual description of it. I'm actually going to get into more detail in the next slide, so I just kind of wanted to show it simply first before I dove into something more sophisticated. So again, we recognize there have been many changes. As I pointed out on the map before, the water projects that are exporting water are down here in the southern part of the delta. So we have this estuary scale of a food web alteration of pretty epic proportions. But then if we get into the central and southern delta where the water projects are, we have yet another set of things that are an interaction of project operations and things that are not related to the Central Valley Project or the State Water Project. And so on the left is that list of other things or other stressors, and on the right is a pictorial representation of the project operations. And I'm going to get into some more detail here. So on the left we have deepening of shipping channels to allow shipping. We have rip-wrapped levees. I should have probably stuck a picture of that in, but sooner or later you'll see one, I'm sure, in the next couple days. We have flooded islands, which are former agricultural tracts where the levees broke and now they're underwater. We have non-project flow allocations in the San Joaquin River and McCollum basins that contribute to low inflows in the San Joaquin side of the delta. And when you put all of those first four things together, what you get is a lot of push from the tides dispersed into a lot of channels in the central and southern delta, and very little inflow. And the result is that although it's kept as fresh water by the Sacramento River, biologically it's basically a lake. It's not really shaped like a lake outside the flooded islands, but the biology is telling you it's a lake. So you have the nutrient and water quality changes that you would expect from that, and you have submerged aquatic vegetation proliferation and a lake-like fish assemblage with bluegill and largemouth bass and those kinds of things. And so those are long-term changes that kind of are part of that baseline. And then sitting on top of that is the water project operations. And what the water project operations are doing are moving water through the delta so that it can be exported south of the delta for agricultural and urban users. And so this picture comes from a paper by Wim Kimmerer and myself that took the California Department of Water Resources DSM-2 particle tracking model and ran it hundreds of times under different scenarios of inflows and exports and tides, and summarized the average result over those this way. And what it's saying for all of these different particle insertion locations that are circles on this map of the delta is a relative scaling of how much of the proportions of particles that ended up being exported by the Central Valley Project and State Project. And so it shows that for the most part, San Joaquin River water, interior delta water, is exported typically. And that typically McCollum River can be exported at a fairly relatively high proportion, as can central delta water, but it's not. Ironically, this water right here around what we call Frank's Tract is on average less exported than the McCollum River water coming from the Sacramento River Basin, and that is a project design. The project was designed to get Sacramento River water across the delta, and that's what it does. And then, of course, water that's out here in the western delta then has less opportunity to be exported except under conditions of very high export to inflow ratios or extremely low, basically high export, low inflow. So this intersection, why do we care about project operations in such a degraded habitat? Delta smelt is rare, like I pointed out. It's had a negative population growth rate for a long time, like I pointed out. Fish entrainment happens at and is observed at fish salvage facilities in front of those pumps in the South Delta. So that's a source of take that we have to think about in an Endangered Species Act consultation, and that take is related to OMR flow. This is a figure that actually came from Rick DeRiso in a declaration in a lawsuit against the biological opinion. And what it's showing on the x-axis is turbidity at Clifton Court Forebay, which is a regulating reservoir in front of the State Water Project, and then daily Old and Middle river flow on the y-axis. And the red dots are days where there's no salvage of Delta smelt during the winter. And the blue dots are days there is salvage, or there was salvage of Delta smelt that are scaled to a normalized salvage density. So how many fish were salvaged per amount of water exported per the prior year's fall midwater trawl abundance index. And so the point being made in this plot is that under conditions of low turbidity and or low old and middle or less negative old and middle river flow, that salvage is rarer than the opposite set of conditions when the water is turbid, because turbidity is a habitat attribute for Delta smelt, and more negative old and middle river flows. And so we recreated this plot to show positive old and middle river flows in it as well. So this is kind of the same thing, except with the full range of old and middle river flows in that time period. And it does help make the point that turbid and positive old and middle river flows, or seaward old and middle river flows, are not as frequently associated with Delta smelt salvage or entrainment or take as turbid and negative old and middle river flows. So that's all part of the equation. And then there's a second part which has to do with habitat suitability. And the reasonable and prudent alternative in that biological opinion handles that in a couple of ways. It does it with delta outflow, it does it with tidal marsh restoration, but also old and middle river flow comes into play here. And this cartoon is kind of foreshadowing what that's about. It has to do with Delta smelt spawning and their ability to successfully spawn. I should be more specific. So again, with the simplest of conceptual models, in the contemporary system in the fall, Delta smelt's an annual fish. The juveniles are starting to get close to sexual maturity, and they hang out in one of two basic places in most years. The low salinity zone, which tends to be around the confluence of the Sacramento and San Joaquin rivers, and then the Cache Slough lower Yolo bypass area, which is the last really turbid freshwater part of the delta. And then from there, it starts raining in the winter, and, you know, sometimes, yes, okay. Sometimes it starts raining in the winter, more often than not. And that's a cue for fish to start moving, thinking about spawning. And so they can move in quite a few directions, including no direction, if we get into the details. So we think that most of the fish that were already residing here are probably going to spawn in that general area, probably not going to go too far away. But these fish that are in the low salinity zone have some decisions they can make. If it gets really wet, they might be advected downstream and go spawn in Sassoon Marsh or even the Napa River, which we have otolith-based evidence that they can do. Or they can go upstream and join their friends up here in the lower Yolo bypass, or they can move up the San Joaquin River, which is a riskier strategy. So again, reminding ourselves, what is old and middle river flow? It's flow in these channels, and as I said, it's often thought about as a net flow. Well, what would a net flow have to do with an adult fish that's swimming? Maybe not very much, except under extreme conditions. But Old and Middle River flow is tidal. And so this is just one example. This is December of 2012. And this is a frequency histogram of Old and Middle River flow measurements at the USGS gauges and their frequency of occurrence. And so white bars are ebbing flows that are moving toward the bays, and negative values are flood flows that are moving towards the water diversions. And during the month of December 2012, the average Old and Middle River flow was very near minus 5,000 CFS, which is why I picked this particular one. On either side of zero, the graph is scaled the same, from positive 20,000 to minus 20,000 CFS. And what you can see is that the tidal velocities are skewed toward faster values on the negative end, or toward the pump end, than they are on the ebbing or toward the bay end. Why would this matter? Well, delta smelt, most of them are in the vicinity of 3 inches long. So if they're going to move upstream against big tidal flows and big winter outflows, they're going to have to use the tides judiciously to do that, and that's what we think they do. We think that they tide surf, which generically speaking means you get out into the channel in the flood tide and let that carry you in an upstream direction, and then you get out of the velocity on the ebb tide so that you aren't displaced downstream very far. So if you did this in Old and Middle Rivers, what would happen is you'd experience relatively rapid flood tides toward the pumps, then you'd get out of them, and then you'd go in, and you'd experience those relatively rapid flood tides back toward the pumps. So it will all come down to, what is your rules for starting and stopping, and when have you decided you've gone far enough? And I'll touch on that more at the end of this talk. I think I had another point to make, but I lost it, so I'm going to move on. Why do we care? Getting back to that. The U.S. Fish and Wildlife Service started studying the Delta actually right after World War II because they were interested in the Central Valley Project coming online. It came online in the early 1950s, and they went out and they started trawling for striped bass and salmon, but they happened to accidentally catch what they considered pond smelt at the time, and they just stuck all that raw data in tables in the back of their report. And so it turns out that they did sample at least part of the spawning distribution of the 1948 year class of Delta smelt when it came into the Delta to spawn in the winter of 1949. And this is a pie chart that kind of breaks that spatial distribution down. So 35% in the South Delta, which would be Old and Middle River flows or places very near the modern pumps. This is before they existed. 38% in the San Joaquin River main stem, where they still may or may not go that way. So a big fraction of what was collected came out of that region. Then in 1964, the California Department of Fish and Wildlife kind of repeated this sort of thing. And when they did a fall survey of fish distributions, this is the pond smelt, again, distribution, a big dot around Decker Island on the lower San Joaquin River. We don't know what was out in the bays, but we do know there was a big dot there, and then we know when they went back in the winter that these fish had dispersed into that zone that the particle tracking modeling indicates would be southbound much of the time. Oops. Got to use my fake animations here. So this is this year's, and this year's is fairly typical of what we see in the contemporary system, and that is not really any delta smelt in that place where a large fraction of them seem to used to go. And this is February and March Kodiak trawl surveys that are done by the California Department of Fish and Wildlife, and it would seem that although the spatial distribution is the same in both of those surveys, that maybe some fish had migrated between February and March from the Sassoon Marsh up into the lower Yolo bypass area. So do we think that they're not there because of project operations? Well, not in and of themselves. Again, we come back to this slide I showed earlier. There's a whole litany of habitat problems that would tend to make that not extremely hospitable to delta smelt compared to what it was probably like 50 or 60 years ago. But project operations, like I showed earlier, do affect take and probably affect habitat suitability by directing flows toward the pumps. And so here's a more sophisticated conceptual model. This is where we're going with this for our collaborative adaptive management process that we're embarking on now. This kind of lays out alternative potential conceptual models of how to think about this. And just to walk people through this, this is an adult delta smelt at the low salinity zone, and it's got a decision process about where to go. If outflow is very high, higher than some threshold that we haven't started to define yet, it's probably going to advect west and go spawn in Sassoon Marsh or maybe even the Napa River. Its probability of entrainment in the South Delta is functionally 0. If the fish is up in the lower Yolo bypass or it stays in the Sacramento River heading that way, it also has a probability of entrainment, at least in the South Delta, that's functionally 0. And its decision process could be a function of tide, turbidity, tide and turbidity, tide, turbidity, and something else. The idea is to test these alternative conceptual models to refine this. If that fish decides to swim up the San Joaquin River, then its probability of entrainment begins to get bigger than 0. And it has the same kinds of decision processes that have to be examined in more detail. Then, if it swims into the San Joaquin River, it has some probability of moving into old and middle rivers, at which time its probability of entrainment is going to get quite a bit higher than 0, as far as we can tell. And the laundry list of potential factors gets broader, but most plausible conceptual models, most credible conceptual models, would suggest that old and middle river flow has to be part of that decision process that those fish are trying to navigate. And again, reminding people that this is a tidal time scale issue for a migrating fish, a tide surfing fish. So we recognize that. I think I just want to reiterate that. And point out some basic factoids that come from particle tracking model. Not that this one-dimensional particle tracking model is sophisticated enough in and of itself to do this, but it can point out that it doesn't necessarily matter that it's, well, I'm going to just say what's in the title, I think. If I stick a neutrally buoyant particle down here at Chips Island, unless there's an extreme of exports and extreme low inflow, none of those particles would ever wind up entrained down here. However, if I put a tide surfing particle in here, which Ted Summer and I and a few people have done, then it's going to swim upstream against even very high net delta outflows. And so what it's going to do that's different from a neutrally buoyant particle is experience this condition, and then this condition, and then this condition, and then that condition, and then that condition, if it goes that way. But the probability, again, being much greater than 0, unlike a neutrally buoyant particle. So I think old and middle river flow is still highly relevant, even for a fish that is swimming and making behavioral decisions. At that, just to remind the panel that the real punchline here is old and middle river flow is, in the Fish and Wildlife Services, the best available hydrodynamic indicator of the entrainment risk for delta smelt. Take-home points, we recognize it's a clams estuary at that scale, but the OCAP biological opinion is about water project operations and how they interact with delta smelt biology. And one more time with that punchline, so I won't say it again. And just for awareness, there's quite a bit of relevant literature that has, especially a series of papers in San Francisco estuary and watershed science that have come out mostly since our biological opinion, that have discussed what the degree of entrainment is quantitatively on delta smelt, and a whole bunch of papers that have tried to look at the multiple factors that are influencing their population dynamics, including but not limited to water project operations. So, thank you.
So we're running a little behind. So if somebody has a really critical question right now, you can answer it now, or Matt, you're going to be around for the rest of the day. So we do have a session, I don't know if I pointed this out earlier, towards the end of the day where you'll have probably 45 minutes or so, and you can circle back to any of the presenters during the day and ask any of those critical questions. So, who are you? Oh, yeah.
It's hard to tell when it's on.
How about now? I apologize for being late. Delta Airlines decided they couldn't fly certain routes, and that was one of them, so I overnighted in Salt Lake City. I woke up very refreshed, and now I'm ready here, so I apologize for coming in late. I'm Kenny Rose from Louisiana State University. I'm a professor there in oceanography and coastal sciences, and I'm not sure what other introductions people made, but I will add I'm also a member of the Outflows panel that parallels this one, and I've been on a variety of these review panels and committees, etc. So again, sorry for the dramatic entrance, but traveling's not so easy these days.
Okay, thanks, Kenny. I think if you're okay, we'll go ahead and move on.